carbohydrate chemistry and going through some of the types of carbohydrates, which I know in that thrilling video that everyone has watched multiple times, we went through some of those names and the nomenclature. We'll go through a little bit of that quickly and think about the stereochemistry. The hardest part probably is the conformations, and then we'll get into some of the reactions with these. So where we ended last time was thinking about some of the different sorts of depictions of carbohydrates, such as the bond line structure shown here on the left for glucose. We're not going to really use those structures very often. It's a little challenging. The Fischer projection, which I scribbled in here to the right. Then when we can turn this into a cyclic structure, which is known as the Haworth projection. And then finally, we can turn this into this chair projection. And we're going to do this today, again, and show how we do this stepwise. Stereochemistry is a very important part with carbohydrates because, as you notice here, and I'll use the bond line structure first. The chirocarbon here, chirocarbon here, chirocarbon here, chirocarbon here as well. So we have a lot of different stereo centers. And actually, why don't we come back to that a little bit later, and I'll show you the trick. Maybe you've already seen this, of how to design, or how to designate, I should say, RNS stereochemistry and Fischer projection. Let's do it in a slightly simpler sugar. So first, to review some of the language that was indicated in that video, these two types of carbohydrates that we're going to consider, aldoses and ketoses. And there's really nothing new here. We've been using the language so far of aldehydes and ketones. So we're just going to do the same thing now in the context of a sugar. So let's imagine having a sugar. Let's draw the carbon. So I have 3 carbons. CH2OH here. Let's draw it like this. We're not really showing any stereochemistry yet at this point. And this sugar, just to know the common name for this, it's known as glyceraldehyde. That name doesn't really mean anything other than if one knows the structure of the sugar. You'll see variants of this when you, in biochemistry or in biology classes, you may have already seen it. So this sugar has an aldehyde on the end. So we have this aldehyde up here at the top. So a little bit more in terms of the language of this sugars, we can call this an aldo, indicating the aldehyde. And then we look at the number of carbons. Here we can start with the aldehyde carbons. So 1, 2, 3 carbons. So for 3 carbons is tri. And then to indicate the carbohydrate, the sugar, it's an ose. So I want to call this an aldotriose. The other kind of simple one to show for some of this naming is to stick with 3 carbons, but now rather than an aldehyde, this one here is a ketone. Notice this looks like acetone here. So 3 carbons with this carbonyl group in the middle. So now we've added these 2 hydroxyl groups. So the common name here is dihydroxy acetone. So it's a ketone. And the short name now is it's going to be a keto, 3 carbons, so tri again, and ose, so ketotriose. Let's do 2 more, and now, because we have more carbons, let's think about this in terms of a Fischer projection. Let's get rid of just drawing all of the C's for carbons, and so we'll put, not quite straight, let's try that again, try it at a different angle. A line here, where we'll show an aldehyde. And let's decorate this now with some hydroxyl groups. Squeeze another. Oh, that's pretty close. It's too close. Oh, it's not what I wanted to do. Let's try this. So a little more complicated sugar. I'm not drawing all of the letters C's here in the middle because a lot of times you'll not see this in the Fischer projection. And so the common name for this one is the one that was above. So this is glucose, which is going to be our benchmark that we're covering. This is an aldehyde again. And so in terms of the last part with the name, 1, 2, 3, 4, 5, 6 carbons. So it's an aldo, hex for 6, aldohexose. And let's just do one more. Now, rather than having an aldehyde, let's make that, it's kind of weird, but we'll just put a carbonyl group there. Let's decorate this with a bunch of hydroxyl groups. And like this at the bottom. And this is one more very common sugar. This is fructose. It's a ketone. And so this is going to be known as a ketohexose. So a little bit of new language, but hopefully one can see systematically what's being described. If it's an aldehyde or a ketone, how many carbons, and then the ose indicates the sugar. As a slight aside for those of you who are interested in it, of course, we see glucose a lot in biology in terms of energy. And glucose is a 6-carbon sugar. In glycolysis, it's essential metabolic pathway. It's first going to be broken into 2 3-carbon sugars. And those 2 3-carbon sugars are actually phosphorylated forms of these 2 sugars over here. So it's glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. There's going to be a phosphate group here. Those are the products when glucose gets broken from 6-carbon sugars into 2 3-carbon sugars. And then these 2 are actually interconverted by an enzyme known as triose phosphate isomerase. So it's indicating it's a triose phosphate. It's an enzyme that works with 3-carbon sugars. And isomerase, so it converts one to the other. It actually converts this dihydroxyacetone phosphate into this compound here, which is known as glyceraldehyde 3-phosphate then, which then goes on through glycolysis with an enzyme, glyceraldehyde 3-phosphate dehydrogenase. And that goes through the rest of glycolysis into the Krebs cycle or TCA cycle or whatever you want to call it, and then into oxidative phosphorylation. So you'll see these structures again in biochemistry. Okay, so now let's get to something that's really exciting about stereochemistry. And let's use the same 2 compounds. Actually, sorry, let's use glyceraldehyde. And for this one, let's redraw this. This is the one that has been the common one. Actually, let's just put the carbon back in there for now. Sorry. And this sugar here, we can define the stereochemistry in a couple of different ways. This is historically known as plus glyceraldehyde. This is due to the ability of it to rotate plain polarized light, as one that it's seen in the first semester of organic chemistry. And the designation in carbohydrates is a new type of a designation. This is known as the D stereoisomer, so it would be D-glyceraldehyde. And let's just put its counterpart up there, and then we'll mention a couple of things about the stereochemistry. Sugars can be designated as D or L. So let's draw the L conformation. And the difference here is, notice where the hydroxyl group is. And these 2 compounds, they have only one chiral center. Let's put a little star next to that. This carbon on the top that's part of the aldehyde is not chiral. It doesn't have 4 different groups attached to it, nor does the bottom carbon here on the left side. This carbon has 2 hydrogens. However, the central carbon has 4 groups attached to it. The aldehyde carbon, CH2OH, a hydrogen, and a hydroxyl group. So this carbon is chiral. So is this one. So these 2 species, they have one chiral carbon, and they differ in their stereochemistry at that center. So they are going to be enantiomers to each other. Just to bring back some of that language. There were enantiomers and diastereomers. Enantiomers are the mirror images of each other. And if we were to draw these 2 compounds looking at themselves in the mirror, you would see that they only have inversion at that one chiral center. So they're going to be enantiomers. So in terms of the plain polarized light, the plus, one is plus, or say it rotates light to the right. The other one is going to be minus. So that's a minus in the parentheses, and then minus glyceraldehyde. And the jargon that's used in the carbohydrate world is that there are D and L sugars. So this is L-glyceraldehyde. And I don't think I have all the letters there. Start that one over. So the minus here comes from the, whoops, I meant to point, sorry, not to erase. So the question is, if light is rotated, if plane polarized light is rotated to the right or to the left, is one way it's designated as being plus, say, or minus. And we're not going to really go into that in any detail, but just that you might see this in your reading about carbohydrates, that sometimes it might be called plus or minus as a sugar. So you might see it listed someplace, oh, plus glyceraldehyde. Okay, so while we're on this, a couple of more points is, this was mentioned in that video, so we can go back to it if you want. The language for the D and L is that you put the carbonyl group on the top in terms of the Fischer projection. So the carbonyl group is, say, sitting here, carbon 1, 2, and 3, so on. And so in other words, this carbonyl group is not, say, down on the bottom, flipped around. And then what you do is you go to the furthest, we'll say, how about furthest OH group on a chiral carbon. And then if that OH group is to the right, that equals D. The OH group is to the left, that equals L. So for this particular compound here, glyceraldehyde, we have the carbonyl group on the top of our Fischer projection. We go to the furthest chiral group. Well, that's actually just this one. We only have one chiral group, and we notice it's pointing to the right. And this is for historical reasons, that this has been known as the D version. Do the same thing here, go to the furthest chiral carbon. Now the hydroxyl group is pointing to the left, and so that's the L version. The D sugars, these are the naturally occurring forms. Kind of interesting, actually. All the known carbohydrates are the D form, and the same language also applies to amino acids, and it's actually the L forms of the amino acids that are the forms that are involved in peptides and protein structure. Well, however, there are unnatural configurations. Well, really, unnatural is not the word I should use, but L versus D. There's D amino acids that are actually used in biology as well. But for the sugars, the carbohydrates, the naturally occurring forms are the Ds. So we'll define that for one or two other sugars in a minute. But while we're at it, let's quickly go back to the language of R or S. And let's just assert for a minute, this D-glyceraldehyde, this sugar is in the R, or this chiral center is in the R conformation. So yes, James, you'll see that D here equals R. You are correct. And so then we're going to say this one, if this is R on the left, it has to be S on the right, since they're going to be enantiomers to each other. So how do we actually define that? Let's go down here below the page break, and let's draw a little bit more detail about what this Fischer structure actually represents.